Next numerical method that I'm going to cover is the steepest descent method. Let me start discussion from the comparison methods what we just studied in previous lectures, Newton and quasi-Newton methods, and steepest descent method what we are going to study today. Let me say a couple words about advantages and disadvantages. First, if we talk about advantages of a Newton and quasi-Newton methods, we have to say that clear advantage is speed of convergence. We remember that if we have good initial guess, initial approximation, this method can converge really fast to our solution. If we consider steepest descent method, we have to say that for this particular method, we don't have to know accurate or good initial guess. This method will converge even for very pure initial guess. And this is clear advantage for this particular method. When we talk about disadvantages, we can say that Newton-based methods will converge very fast to our solution, exact solution, only if we have good initial guess, which means that we need an accurate initial approximation, which is not easy to get sometimes. And this is clear disadvantage of these particular methods. At the same time, despite that fact that steepest descent method will converge even for pure initial approximation, it will converge only linearly to our solution. And this is clear disadvantage of this particular method. But by comparing these two advantages and disadvantages, we can say that we can use steepest descent method in order to find good initial approximation for Newton-based techniques, by analogy with bisection method for single equation. First, let me describe a general idea of a steepest descent method. Let's consider a system of n nonlinear equations. Let's construct new function as follows. Function g will be function from n-dimensional real-valued space to one-dimensional real-valued space. And this is our new function. Because this function is non-negative, exist point, let's say x1 star, x2 star, xn star, and not necessarily unique, such that function g at point x greater or equals value of this function g at points x star. And since it's not non-negative, it's greater or equal 0 for any component of vector x from In. As a consequence, if we find somehow this point x star, which is minimizing function g, and if minimum of this function equals to x star and equals to 0, then that point x star will be solution of our system. In other words, equals 0. This is equivalent to this. Before I start describing the method, let me remind you a couple very important definitions from multivariate calculus. But first let me mention that the word gradient means from the Latin word gradi, to walk, which means that we are supposed to walk in a particular direction, what we are going to find as well, in order to find the local minimum of our function. So, first definition is following. The gradient of a scalar-valued differentiable function g of several variables is the vector field or vector-valued function whose value at point x is the vector whose components are the partial derivatives of g at point x. Another definition is about directional derivative of a multivariate differentiable function along a given vector v at a given point x. Directional derivative represents the instantaneous rate of change of a function moving through point x with velocity specified by vector v. In other words, it says how fast function changes in a particular direction. And directional derivative is a special case of so-called Gateau derivative. Let's formulate definition. Suppose that v is a unit vector in Rn. The directional derivative of function g at point x in the direction of v measures the change in the value of a function g relative to the change in the variable in the direction of v. And formula 1 represents this definition. Let me describe the algorithm of the steepest descent method. First, we evaluate function g at an initial approximation x0. Then we calculate the gradient of our function g, where k is the iteration number, and we determine direction from x0 that results in a decrease in the value of our function g. And next we compute next approximation for our vector x using recurrent formula 1, where alpha k represents the minimization step. This is a scalar value. Our iteration method we call gradient descent method because for every iteration k exists alpha greater than 0 such that value of our function g at k plus 1 iteration should be less than value of our function at previous iteration k, which means that with every iteration we have smaller value of our minimizing function. Let me give you some intuition about this method. Actually, there are two main questions: how to choose direction in which you should go, and how to choose alpha. When we want to choose direction, the most logical way is to choose direction along which our function decreases the fastest. And as we know from the mathematical analysis of function of several variables, the direction of the greatest increase of our function at a given point shows its gradient at this point. Therefore, we can accept as a direction of our vector decrease antigradient of our function g, which means that we should accept this direction. Now, how to choose alpha? There are different approaches how it can be done, but optimal step in antigradient direction, we can think about step that value of function g minimal among all values in this fixed direction. In other words, this point should be local minimum. That's why I wrote this formula. Let's say formula 2. So let me describe this approach slightly differently. We can consider function, let's say h alpha, and we want value alpha that minimizes our function h, and this alpha will be what we actually want to find. We can compute minimal value for our function h just by differentiating h and then solving a root finding problem to determine critical points of function h. But this is computationally expensive. Instead, we choose three values: alpha, alpha 1, alpha 2, alpha 3, this way. And we hope that all these three numbers are close to the minimum of our function h. So then we can construct quadratic polynomial which interpolates h at points alpha 1, alpha 2, and alpha 3. And minimum of this quadratic polynomial can be very easy to find, can be easily found. And now we introduce new value, alpha, let's say head, which belongs to interval alpha 1, alpha 3, so that polynomial at this point alpha hat is a minimum in this interval, and we use this polynomial to minimize or to approximate the minimum value of our function h. And then we use this alpha hat in order to approximate next value of our vector x. So we have value g at 0 iteration, our initial approximation is available. In order to start our computations, first we choose alpha 1 equals to 0. Next, we find alpha 3 such that h alpha 3 should be less than h alpha 1. Since alpha 1 we just picked and it does not minimize function h. Therefore, we try to find minimum of our function h. Therefore, exists such alpha 3 which gives us less or smaller value of function h at this point alpha 3 than value of our function h at point alpha 1. And we choose alpha 2 as alpha 3 over 2, just half of alpha 3. It's just our choice. The minimum value of our polynomial p on interval alpha 1, alpha 3 can occur at the critical point of this polynomial or at the right endpoint alpha 3 because of since this one and this. Because px is a quadratic polynomial, the critical point can be found by solving linear equation. Previously, I talked about how to choose the minimization step alpha optimally, but there are alternative ways how alpha can be chosen. For example, very often successful strategy of gradient method can be if we pick alpha as a very small constant. Unfortunately, using this approach, method can diverge. Another way how alpha can be chosen is following. Let's say we pick alpha 1, then alpha 2 we pick as a half of alpha 1, alpha 3 is half of alpha 2, and so on. Every time we just decrease alpha with constant rate. How to pick alpha? It really depends on the particular problem, and sometimes it's not necessarily to have a very complicated representation of alpha. Sometimes it can be just small constant. Let's say a couple words about advantages and disadvantages of gradient method. First of all, I have to say that the main advantage of this method, let me write it down, the main advantage is global convergence. So it means that whatever initial approximation you have, your method eventually will converge to desired accuracy or exact solution. There are a few disadvantages of this method as well. Despite the fact that method will globally converge, it may take a lot of iterations before it will converge. And another drawback of this method is that it's very complicated to find optimal value per step. It can be time-consuming, computationally expensive. For example, if we look at the restricted function as an example, let me change color of my pen, let's say red. We can see that we have global minimum for this function, and we have a lot of local minimums and everywhere. It's like here, here, and here. And we can see that for this particular function, gradient descent method will probably work very, very slow, and we need many iterations to find local minimum. Let's illustrate how this method works using example.
Before I show you how the steepest gradient descent method works for system of nonlinear equations, let me remind you how this method works for single equation, let's say this one, and let's find solution using gradient descent method for this particular equation. And let me do it numerically. So first what I want to show you is how to use MATLAB and visualize our function. Actually, first what I want to create a grid x and y, then function z, in this notation it's function g. This command creates window, just empty window for your plot. This surface, this is exactly what you can see here. And this command allows you to use LaTeX when you write names of your axis or title, doesn't matter, whenever you use it. So once you visualize your function, we can solve it. For gradient descent method, we use this recurrent formula, and we see that first what we need to compute is gradient of our function. In our case, we have function of two variables, means that we should compute partial derivatives. Partial derivative of our function g over x, and we find this derivative using simple rule, and we can get first expression from here. And similar to that, we find derivative over y, and we can also compute it and get second equation.
Now let's write our recurrent formula for every component, for x and for y. And below I provided a piece of MATLAB code. in order to show how simple gradient descent method works. First, I create a new window, and then I want to create contour like that. So in order to see how a solution changes from iteration by iteration. Then I pick initial approximation. In my case it's 1519, which is here. Then, if you remember, I mentioned that there are many ways how the minimization step alpha can be chosen, and it depends on particular problem. Because our problem is not very complicated, we can pick alpha as a small constant. We don't have to use complicated formulas. And this is a number that I picked. Next few lines, this is actually gradient descent method, where I use plot in order to see how solution changes from iteration to iteration. For example, our initial guess is k equals 0. Then at k equals 1, solution will be here, k equals 2 here, and so on. And as we can see, solution converges very fast to true solution. So, and finally we can see the answer, that if we pick k5, this is how far we can get, and the best result for k equals 30, we can approach to our true solution. In this line, I show how to print the results in MATLAB. But you can use function fprintf, and this is a format of a number. This shows just new line. So this simple problem is solved. In the next video, I'll show you how to solve system of nonlinear equations using gradient descent method.